All right. It is 5 p.m. now here in Germany. I think there may be some people still logging in, but I would start with my general introduction already. Again, welcome to our today's webinar. My name is Victoria. I am the host for today, and I'm going to give you a quick introduction before we start our presentation. The webinar today will be recorded for you, and you will receive the video by mail in a few days. Of course, you will also have the opportunity to ask your questions. In your Microsoft Teams window, you should find a Q&A section somewhere at the top or on the right-hand side. The icon for that looks like a speech bubble with a question mark, and the icon is usually titled F&A or Q&A, depends on your language settings. We will answer the questions at the end of the webinar, and if we don't manage to answer everything live, we will definitely get back to you via email afterwards. In this case, it would be great if you do not ask your questions anonymously, so please leave your email address with your question. This way, we can make sure that we can really get back to you with an answer. If you have any other questions, you are also welcome to contact us at any time at our general webinar address, webinar_ngb@netzsch.com. I will post you this address in a second as a message, so you can access it at any time. Now, last but not least, I would like to introduce you to our today's speaker, Dr. Elena Moukhina. Elena studied physics and mathematics at the Yaroslav State University and has a PhD in physics. She has been part of the NETZSCH analyzing and testing family for over 20 years now and has gained lots of experience in our R&D department before taking over the position of the business field manager for the software Kinetics Neo. Elena has been a huge contribution to the development of the Kinetics Neo software, which she will demonstrate today. So welcome, Elena. We are happy to have you here today, talking about our new NETZSCH Kinetics Lite software. I will now hand over to you, Elena, to get started. So enjoy our webinar and have fun. I will be back for a short Q&A at the end.
Thank you very much, Victoria. And now we have our webinar, Easy and Fast New NETZSCH Kinetics Lite software. Let's go to our agenda. We have introduction, then we have some automatical data transfer from Protos to Kinetics. And I would like to show you live in our software how it works. It's really fast. Then we have basic evaluation in Kinetics Lite, activation energy, model-free kinetic, single-step kinetic analysis, selection the best kinetic result from different methods of kinetic analysis, then predictions in Kinetics Lite, dynamic, isothermal, lifetime, comparison Kinetics Lite, new Kinetics Lite software and Kinetics Neo software, advantages of Kinetics Neo, and then a few final slides. Let's go here. If you or your students are the beginners and have make a few new steps in kinetic analysis, then you just start probably with the evaluation of activation energy. What is the activation energy? And you could find the activation energy as a value, for example, for single step kinetics. This is the really first task or first problems which could be solved by kinetic analysis. It's not complex, but it is the first one. Then for nth order kinetic, it's necessary to find reaction order of autocatalysis for autocatalytic reaction. If you have crystallization, for example, isothermal crystallization, and they works according to nucleation equation, Avraman nucleation equation, then it is necessary to find dimension of nucleation. If the process is not really single step and there is some changing of the process mechanism during the time and during the reaction progress, then the activation energy could be found not as a value as it originally done for single-step kinetics, but as a function, the function of conversion. Conversion is a value which is changed from 0 to 1 and show how our reaction goes on. Before reaction alpha is equal to 0, and after then it is, after a reaction is finished, it is equal to 1. The simplest case, isothermal predictions for given heating rate, half-time predictions, so predictions of the half of reactions, or maybe lifetime predictions for given value of alpha. For example, for decomposition of polymers, normally we speak about 5% of conversion. So if during decomposition polymer has less than 5% of conversion, then usually it is more or less stable and can be used for the future. And if the degree of conversion or decomposition is higher than 5%, then material is has another properties and cannot be used anymore. And here it is very important to know at which temperature, for which time, at which time the 5% of conversion will be found. These are really the first problems which could be solved by kinetic analysis for the people who just start to work with kinetics. And if you are expert, then you have some additional problems. You will find that not all processes are single-step processes. More than 90% of them are multi-step kinetics. And the steps inside your materials are connected differently. It could be independent step, consecutive steps, competing steps. It could be also backward reactions, or we have reversible reactions. And you must find each step, and you must file detailed information for each step, kinetic parameters for each steps, and to find how the concentration of each reactant will be changed, including intermediate reactant. Sometimes you can find that the kinetic is totally not arrhenius, as it was at the beginning, assumed at the beginning. For example, if we speak about curing with vitrification, then we can find that there is a glass transition, and the glass transition will change our curing mechanism. And this glass transition is not a constant value, but it is changed during the reaction progress. And we must find where the vitrification and how a reaction mechanism will be changed. For example, for crystallization during the cooling, it is also non-arrhenius kinetics, because we must take into account the glass transition and the temperature and the melting temperature, and our crystallization happens only in this range. It could be not above melting point and not below the glass transition temperature. And if we have very fast cooling, then crystallization is not complete, and we must take into account such things. Sometimes not only the temperature play a role for kinetics. But also the pressure, and for example, the kinetic the rate of chemical reaction depends on the pressure, on ambient pressure of inert gas, or it would be the partial pressure of active gas, for example, pressure of partial pressure of hydrogen or oxygen. For photopolymerization, we have additional parameter is UV intensity, the intensity of UV light. The higher intensity, the faster polymerization. If you have double component reactions, then the mass ratio of reactant play a role, and kinetics depends on the ratio of masses of both components. We can make predictions not only for isothermal conditions, but for any temperature program. We must find conversion, concentration, reaction rates. We can calculate time temperature transformation diagram in order to see where we have vitrification line, where we have gelation line, where is gelation point at any temperature conditions. And it could be also optimization for industrial temperature profile. So here we have very simple questions for beginners, very, very simple, and some more complex. And therefore, we have implemented two types of software. The first is the new one, is Kinetics Lite software. It is really fast and easy, and it works for beginners only. And it has only basic kinetic evaluation, which was in the first step. Another type is the Kinetics Neo software, which exists up to now since many years. It is a really powerful tool and comprehensive and can answer the questions or help you to find the process rate for the really complex reactions. It could be used for beginners and for experts as well. Now we would like to present you the Kinetics Lite software. The first question, how to find activation energy. For example, if we have TG and the mass of material will be changed from initial mass to final mass, and we have a total mass loss and the current mass loss in the current point, then the ratio of the current mass loss to the total mass loss is the value of alpha, which is conversion and change from 0 to 1. If we speak about DSC, then we have at each point the partial peak area from the beginning to this point, and if we make a ratio to the total peak area, then we have alpha, which is changed from 0 to 1 during our reaction. This is our degree of conversion, and it is changed from 0 to 1, independent from the type of the data. And the rate of degree of conversion or reaction rate, the alpha over dt, where we have our alpha is conversion, has dependence on alpha, for example, for different reaction types, nth order reaction, autocatalytical reaction, nucleation. Each has pre-exponential factor, its collision frequency, and dependence on temperature is according to Arrhenius. And here we have the activation energy, and activation energy is the difference between the energy of reactant and energy of transition state, which has a molecule over the chemical reaction. And now the question, how to find activation energy. Here we have nth order reaction, and we have our standard software. It is the Protos analysis software, and here is our nth order reaction. Question, how to find the activation energy and the order of reaction. Could it be fast? Could it be found fast? Firstly, I would like to switch on to our software, standard software, NETZSCH Protos thermal analysis. If you work with NETZSCH instrument, then you know that you will get this data after measurement. So here we have three curves, three measured curves at 20K per minute, 10K per minute, and 5K per minute. And firstly, I would like to remember you how it works in the old software without our integration between Kinetics software and Protos analysis software. So up to now, it was necessary to take each curve. After that, you should go to export this curve to file. You should select the evaluation range. You must check here all fields. If it's TG, if it's spline or original, you must set a number of points for export. It should not be too few points, because then it's not enough for good analysis. It must not be a big value. For example, it could be 500 points. Then you must check a format, say export, and then put some file name, for example, TG1. It is the first curve. Save. We can open the file, see what we have here, temperature, time, mass, and a lot of data here. After that, we must go to Kinetics Neo software just to select here data type for our kinetic analysis, for example, thermogravimetry. Then we must go and search our new file, open it, just to check if here the first column is temperature, yes. If the units are correct, yes. The second is time, yes, and the units correct. The last is mass, is correct. And after that, we must make import. And then, for example, for DSC, we must make a baseline and so on. So that was up to now, and we must repeat it for each curve. And only after that, we can make some analysis. And now let's go and see how it would be work in our new software, in Kinetics Lite software. You can really see if it's easy or not, or you can just count the clicks. First, select all curves. I just make a click on the axis. Then we can evaluate mass change, say apply, OK. After that, we can go to Kinetics Lite software and make nth order reaction, nth order kinetic. Ready. Here is activation energy, 75 kilojoule per mole, pre-exponential factor, and order of reaction 0.38. So that was, according to my count, about 6 clicks. And it is really much easy and much faster, which was up to now. Now, for example, the software can estimate from the curve shape what is the reaction type. And here, nth order reaction is selected automatically according to the shape of reaction. And then all parameters for nth order reactions are shown. Here, if we go to our presentation, let's go here, we just make a click either from toolbar, or we can go to extras menu item and select Kinetics Lite in the menu. It's up to you. And after that, we have immediately, with one click inside Kinetics Lite, we have all results. Next question, we have autocatalytic reactions. What are the activation energy, pre-exponent, and order of autocatalysis? Now, it should be autocatalytic reaction. For example, for curing, here is epoxy curing. We have N is the reaction order, we have activation energy, we have order of autocatalysis. Here is pre-exponent for autocatalysis. Let's see how complex or how easy it could be done now in our Kinetics Lite software. I will just go back to our standard software, NETZSCH Protos thermal analysis. We just select our data. Here are 3 data with exe up. And now let's make kinetic analysis. First, select everything. Then evaluate peak area with the baseline, for example, tangential baseline. Apply, OK. Go to kinetics and make single step kinetics. Ready. So here you can see almost OK. It's 0.999998. The R square. We can make one additional click just to optimization of parameter. And now we have a perfect result. What software did? Firstly, the data are transferred directly from Protos analysis to our Kinetics Neo. The baseline is subtracted. After that, the software Kinetics Lite analyze a shape and found automatically what is the type of reaction. In this situation, automatical type of reaction is CN. This is the reaction type for autocatalysis. We have here pre-exponent of autocatalysis. We have activation energy, order of reaction. And now we can use this model, or you have very simple evaluation for kinetic parameters for single-step reaction. Let's go back and see what is necessary. That was, again, less than 10 clicks in order to find all parameters for autocatalytic reactions. Sometimes it is necessary to make not a single-step reactions, but model-free, use model-free kinetics in Kinetics Lite. There are different methods. Some of them are single-point model-free methods. For example, STM E698, E2890, E1641. Here, all these methods are created in the last century and based only on 1 point before the modern possibility of the personal computers were present. And one of them, for example, take only 1 point for each curve. Here is the maximum point. After that, and all other information is lost, then these maximum points are present on the Arrhenius plot, where we have horizontal axis 1 divided by absolute temperature. Vertically here, for Azawa method, is log of heating rate. Then we have a straight line. All points are on the straight line. And a slope is proportional to activation energy. So from the slope, we can find activation energy, and it is only one value, and it is a really very, very fast example. Now the question, can we find activation energy from single point model-free methods? Let's go to our software, where we have already single-step kinetics for autocatalytic reaction, and make model-free kinetics with the method STM698. Here is Azawa method only for maximum points. Now we have our straight line, it's 1 click, and here we have activation energy is 53 kilojoule per mole. Is it good? Is it correct? We can just see here the conversion fit. Is it good? So it is not so good as our model-based kinetics. So here the fit is good, R square is 0.999, and at that time it was R square is 0.89. So it is really not good. What is important? You must always see the fit. I know that sometimes the people just calculate very, very fast according to model-free kinetics, single point model-free kinetics, just take a maximum point, make estimation of activation energy and think, yeah, it's a result. But you see, it's not result. It's very, very, very roughly example result, and this result is not the result which could be go to some publications, and in any case, it cannot be go to some real problems with some industrial problems where the results of kinetics must be very, very fine and with the less error, calculated with the less error. Now we are here again. If we make go from data, from our Protos analysis, put data, transfer data to kinetics and make only 1 click, then we can find activation energy with R square and with the fit. And in this case, we must always compare our results. Next type of methods in Kinetics Lite, the model-free kinetics, which are multi-points model-free kinetics. Here, the different points are taken into account. For example, for alpha 0.5, where we have only 50% of total area, we have some points, we have a straight line, we have the active slope, activation energy for 50% of conversion. We can take a points for 80% of conversion where alpha is equal 0.8, and we have a new points, we have another straight line, we have activation energy at at alpha equal 0.8, and we can make it for different values of alpha from 0 to 1, and finally result is a function where we have activation energy as a function of alpha. There are different methods, Ozawa-Flynn-Wall, Friedman, and Wisowkin, and they are included in Kinetics Lite. So this method could be used if the mechanism, kinetic mechanism, is changed during the process. Let's go here. For example, if we have epoxy, double-step epoxy, here is the beginning of reaction. We have one step. At the end of reaction, we have another peak, and here probably is another value of activation energy. And now the question, what is the activation energy for complex process? How fast could it be calculated? We can go back, just see our data for epoxy, for double-step epoxy curing. Here peak area is already found. We just go to Kinetics Lite, have our data where baseline is already subtracted. We can go, for example, for Friedman analysis. Here are our lines. We can see fit. We can see R square 0.9997. We can go, for example, for Wisowkin analysis. Here is also not bad, 0.998. We can go to Ozawa analysis and make fit. So here is not really very nice. R square is less. We can just make another single step analysis, and for total collection, we can make a model-based analysis where we have single step model for this complex experimental data. And after that, we can go to model summary and compare all results. We can make sorting according to the R square. And here the best one is Friedman. It has R square 0.99975. And we can just see it. Here is our best result, and we can just see how it looks like. We have experimental data and we have our modeling, and we can use this modeling for predictions and for other purposes which are necessary. That was very fast. It is very fast and very easy. Again, one click, we have data, additional click, and we have activation energy as a function of activation energy as a function of conversion. I think I have forgot to show you. That was this one. And we can see activation energy as a function of conversion. Okay. And now we have a best fit. We can compare data and so on. What is important? That model-free kinetic may not be used always. There are some rules where model-free kinetics cannot be used. We have some webinar last year. It was, I think, in November. You can find it on YouTube. You can find it on our website. And here are a couple of slides which shows where model-free kinetics may not be used. For example, if you have different values of a total mass loss or different values of peak areas for different heating rates, then you have competing reactions. Model-free approach doesn't work. If mechanism changed is not always at the same value of conversion, then model-free approach cannot be used. Actually, here, these curves, they are not simulated curves. They are real experimental curves, what I show here. Next, for example, if we have a peak directions of different peak directions, some of them are exothermal, some of them are endothermal. Model-free kinetics doesn't work. Cooling crystallization doesn't work because the peak area here could be changed for this data, changed from 3.3 joule per gram up to 38 joule per gram, is not always constant. Because if we have very, very fast cooling and we go very fast to the glass transition point, then no crystallization happens after glass transition point and crystallization is not complete. Sometimes reaction is not measured up to the end. In this case, we don't know what is the mass loss for 100% of conversion. And again, model-free kinetic doesn't work. In this case, only kinetics neo can be used because this is not a basic kinetic evaluation and it could not be used in Kinetics Lite. Next example, pyrolysis. Here is a really complex thing. We have water release. We have decomposition of hemicellulose, of cellulose, and at the end we have lignin. So this is really a lot of different peaks. Here we have decomposition of olive stones. And let's go to our data. Here, pyrolysis. We have our TG data and we have our DTG data, the first derivative. And now let's see if it's fast, how fast or how easy to make kinetic modeling for this really complex data. Firstly, we make analysis, make the calculation of the mass change. We can take into account the first step with the water release as well. Here our data, apply, OK, Kinetics Lite. We are inside. We can make analysis according to Vizovkin. So it is nice. We can make analysis according to Friedman, see the fit. It is also nice. And after that, we can compare them and see the best one is Vizovkin. Here, Vizovkin, we have very nice solution. We have activation energy as a function of conversion, and we can use this result for predictions and for all other things which are necessary. That was pyrolysis, one-click result. Now we can make predictions of our data. It could be dynamic predictions, isothermal predictions, lifetime predictions. Dynamic predictions, for example, for given heating rate. What will be decomposition at heating rate? Let's see, 0.5 K per minute, which was not measured here. Isothermal. What will be the prediction, isothermal predictions for some given temperature? And lifetime is the question, at what temperature material has 5% of conversion after 10 days? Let's go and see how it works. Now we just go to polymer decomposition, select mass change, go to kinetics, make our data, select which one is the best one. The best one is Friedman in this case. 0.99991 is R squared. Now we go to dynamic predictions and see what is the dynamic predictions for 0.5 K per minute, maybe also for up to 200 K per minute with factor 2. So it will be 0.5, 1, 2, 4, 8, 16, and so on, up to 200. And we will start from 200 degrees C, make calculations. Now is our result. We see what happens at 0.5. We see what happens at 64, at 128, and so on. That was dynamic predictions. Isothermal predictions, I will just switch to time. Now we will make, for example, initial temperatures between 300 and 400, and with the step, isothermal, from 300 to 400 with 20 degrees between them, and we will wait, for example, 10 hours. Here is a result for 10 hours for isothermal decomposition at different temperatures. We can make step, for example, 10 degrees C, and we have for each 10 degrees C for 300, 310, 320, and so on. That was isothermal. And now our last questions: at what temperature material has 5% of conversion after 10 days? Let's go to isothermal lifetime. We will say here, we will search between 100 and 400 degrees C. We don't know at which temperature. We have some range, and we will try to search, and then it will be 10 days. 1 day is 1440 minutes, and 10 days is 10 additionally. Calculate, and now we must find 5%, only 5%, this one. Here we have solution. Horizontally is 1000 divided by absolute temperature. Vertically is our time. We have maximum value is 10 days, and the last point shows that show us the temperature for 5% of conversion, where material has 5% of conversion after 10 days, and this is the last curve. The last point, 196 degrees. So we have found the temperature at which material has 5% of conversion after 10 days. So it is relatively easy. Now we can go here. We have found everything, and it works nice. And the next one is isothermal crystallization. Here we have crystallization of polyamide 12 at the temperature, different temperature. What is the difference here with the chemical reactions? For chemical reactions, a reaction will be faster if we have higher temperature. For crystallization, it is another direction. Crystallization will be faster if we have lower temperature because of the supercooling. And after that, let's answer the question: at what temperature polymer needs 1 hour for 50% of crystallization? We just go back, select our polyamide 12, which are real measurements at different temperatures. We can, here the peak area is already evaluated. We can just go to software, to Kinetics Lite, switch to time, make model-based kinetics. In this case, a software analyzed a shape of the data and found that here we have AN reaction type. It is Avrami, corresponds to nucleation during crystallization. And now we will use this data for simulation. We use isothermal lifetime. We will select between, for example, 160 and 175 degrees C with the step of 1, and it will be about 1 hour, 60 minutes. Calculate. We have something here, and now we will select only for 50% of conversion. It is half of crystallization here. These are our result. We have only 50% of crystallization at different temperatures and a maximum at the last point is for 60 minutes, and it is this point 171 degrees C. So we have 1 hour. The crystallization will be 50% after 1 hour for the temperature 171 degrees. So that is really fast to find these values, and we can make it with Kinetics Lite very fast. Here on the graphic, we have half of crystallization and 5% of crystallization. Here is not a problem. And now, Kinetics Neo and Kinetics Lite. Kinetics Lite for beginners only contains only basic kinetic analysis. It uses NETZSCH Protos analysis license, so it could be installed on several computers in the same department. So on the same computers where your Protos analysis is installed, it maintains the Protos support policies. If you would like to make some consulting, they are extra. They are not included, and it works for NETZSCH data only. Kinetics Neo, it is not for only beginners, but it is for experts as well. Not only for experts, for both of them. It contains additionally advanced kinetic analysis. It is 1 per seat, 1 per computer. It includes 12-month support, including free consulting. It works for both kinetics, NETZSCH, and for both NETZSCH and non-NETZSCH data. Lite has only TG DSC. Kinetics Neo has additionally dilatometer, DA, viscosity, arc data, arbitrary differential data like mass spectrometry, reaction rate, arbitrary integral data for storage modules, concentration, sparse data. Each can use additional parameter like pressure or intensity of UV light reactant ratio. For model-free kinetics, Lite has 2 groups for single points and for multi-points kinetics. And for Kinetics Neo has additionally single point dynamic Arrhenius, isothermal Arrhenius, and multi-point STM 2070. Additionally is Kissinger, Akahira-Sonoza, and now our NETZSCH numeric optimization, where we make additional optimization of a Friedman solution in order to have it better. Kinetics Lite has 3 groups of single-step analysis. It is only for single step. For nth order reaction, 3 first, second, and nth order. 4 for autocatalysis, including Kamal-Soror, and 4 for nucleation. Kinetics Neo has a complex reaction where we have several reaction steps, and there is any combination of them. It could be competing, it could be parallel, it could be one after another consecutive. The optimization of model could be done not only for signal, but for conversion rate as well. We have additionally a reversible reaction and phase boundary reaction. We have a group of diffusion reaction. For autocatalytic reactions, there are 3 additional reaction types, including Shostak-Berggren. And for crystallization, we have crystallization for cooling, including Nakamura crystallization and Sbirazzoli crystallization with Hofmann-Lorentz theory. For predictions, here for Lite, we have only isothermal lifetime and dynamic. For Kinetics Neo, we have many different predictions like adiabatic, climatic, time temperature transformation diagram, external temperature profile, and we can make an optimization of a temperature profile for industrial applications. Sometimes Kinetic Lite cannot work for very complex situations, and here I would like to show a couple of them. For example, for double-step kinetics, our Kinetics Neo can show each peak. Here you see separately. Then it can show the concentration of each reactant and product, and also for intermediate reactant during reaction. It can make analysis for a situation where we have steps of different direction, exothermal and endothermal together. Here is one step and here is another step. And it could happen, for example, now we make a lot of analysis for a battery, for decomposition and stability of the battery materials. And decomposition has always such situation where we have exothermal and endothermal effects together. So I have still up to now have no situation where only exothermal effects are present. Also, Kinetics Neo can work with non-Arrhenius kinetic. For example, time-temp construction can calculate or construct a simulation for time temperature transformation diagram. And here we have gelation line, vitrification line, and we can see where material is liquid, where it is elastic, where it is Zoll-Gel, where it is rubber or maybe glass, and so on. We can make the predictions according to the temperature, complex temperature program, not only for DSC or for conversion rate, but also for evolution of the glass transition. In this case, only Kinetics Neo is necessary, and Kinetics Lite cannot do this. Crystallization during the cooling and, for example, isothermal crystallization close to the glass transition. Kinetic Neo can do some things which are impossible in kinetics, like, for example, kinetics of shear viscosity. Here, rheology, we have a data for 2K per minute, for 2K per minute and for 5K per minute. And then after we have a kinetic model, we can make predictions for given temperature program, for this complex temperature program, and we can calculate the value of shear viscosity, how the shear viscosity behave during this complex temperature program. We can make the same for ion viscosity measured by dielectric analysis. We can work with external parameter like UV intensity. Here for low intensity, it is slow. For high intensity, it is fast. It is one kinetic model. It could be also measurements at different partial pressure of active gas, oxygen or hydrogen. Here is the metal reductions and different partial pressure of hydrogen. A lot of hydrogen, 100% reaction is fast, reduction is fast. If you have less value of hydrogen, then reaction is slow. If you have no hydrogen, then no reduction is present. Here we have a reversing reaction, and if we have a high partial pressure of CO2, then decomposition is suppressed and decomposition happens at high temperature. Without CO2, without carbon dioxide, decomposition happens at early temperature. We can make a simulation for different mass ratios for epoxy and aniline, for example, 1:1, 1:2, 2:1. And here we have a data with 20K per minute, but there are different curves. You can find all information about Kinetics Neo on our Kinetics Neo website, kineticsnetch.com. You can find information about Kinetics Lite on our Kinetics Lite website, kineticsLite.com. And you can find a table of comparison between Kinetics Lite and Kinetics Neo if you select features on Kinetics Lite website. Summary. Now we have a new software, Kinetics Lite, can be delivered from July 2026. We have integration to NETZSCH Protos analysis, and it is done, of course, not only for Kinetics Lite, but for Kinetics Neo as well. For Kinetics Neo, it works with Protos analysis version 9.10, and for Kinetics Neo version 3.8. So both of them will be released in July 2026. If you have our NETZSCH instrument and you have Kinetics Neo software, you must just wait until July, and then you have very fast transfer of data from Kinetics, from our Proto software to our Kinetics Neo. And if you have our instrument and still have no Kinetics software, then you have a possibility you can get Kinetics Lite or Kinetics Neo, depending on your tasks. If you have already Kinetics Neo but still have no our instruments, then you can just think for the future to purchase Kinetics, to purchase NETZSCH instruments and to have very, very fast analysis and to save your time. Now we have automatic selection of reaction type for single-step kinetics, again for both single Kinetics Neo and Kinetics Lite. And additionally, Kinetics Lite contain many functions which are typically not present in kinetic options of a standard analysis software for thermal analysis. So if you take alternative standard analysis software, then usually there is no simulated fit and no R-squared. And now you have seen if it is not present, then there is some problems to see if this kinetics are really correct or not. So that's all from my side. And now I'm ready to answer your questions.
Great.
Victoria, yeah,
Yes,
could you please manage it?
Yes. Thank you very much, Elena, for the insights and the great presentation. We actually already received some questions, which we will take care of in a second. To all of our attendees, please feel free to use your Q&A icon and the function behind it right now. So let us have your questions. We will answer them right now. And in case you have any questions, requests, or whatever after the webinar, you can also reach us at our general webinar address, webinar_ngb@netzsch.com. I have already posted this address as a message. So, Elena, I think we take care of the first question. I will read it out loud for everybody. Can we make predictions for isothermal aging at moderate temperatures for polymers with the given TGA data through this software? Can you help us out here?
Generally, yes. We can speak about aging. So for polymers, for polymers. So what is important? That the material must be measured at the same state, not above the melting temperature. Because if you have the composition which is measured above melting temperature, then you have the composition in liquid. And then the composition in solid below melting temperature will be totally different. And in this case, if you would like to make such kind of predictions, you must have a data of decomposition of polymer, experimental data, below melting point. So it should be kinetics for decomposition in solids, and then you can make predictions for decomposition in solids. And what is important as well, if you would like to make isothermal decompositions, simulations for isothermal decomposition, then it is necessary that your experimental data must contain isothermal data as well. Okay.
All right, thank you very much. The next question. Is it possible to import thermal analysis data obtained from instruments other than those manufactured by NETZSCH in order to process the data using the Kinetics software?
For Kinetics Lite, it is impossible. Kinetics Lite works only with NETZSCH data, and Kinetics Neo works with both NETZSCH data and non-NETZSCH data. So if you have an instrument from other manufacturer, then you have to export your results in the ASCII file, in text file. It must contain 3 columns, time, temperature, and signal, for example, TG signal or DSC signal. And after that, you can import this data into Kinetics Neo software. So it is possible for Kinetics Neo software.
Okay, thank you. The next question, how do you find the pre-exponential constant A? Can you tell us more about it here?
Yes, we just, for nth order kinetic, we can calculate pre-exponent according to the best fit. Just the software will find pre-exponent to have a best fit of pre-exponent and activation energy in order to have a best fit of simulated data with pre-exponent and activation energy and our experimental data. So we just, I will go back to our curves. So here we are inside. And we have here, firstly, is our experimental data. Here is experimental data, and here is our fit. And this fit is calculated from activation energy and pre-exponential factor, and reaction order, and so on. So for this temperature program, and the software try to find activation energy and all other parameters, including pre-exponent, in order to have a good fit for all experimental data which are measured at different experimental conditions. And if we speak about model-free kinetics, then, for example, for ASTM, it is written directly in the standard how it should be calculated, and we calculate according to the standard. Regarding the Friedman, we have a glossary on our website, kineticsnetch.com, and all mathematics is written. So we have a straight line. From the slope, we can find activation energy. And if we prolong this straight line to the lower value of 1 divided by t, then from intersect, the value of activation of pre-exponential factor could be found. Okay?
Okay, thank you. And then I think this could be the last question for today already. It's about the price of your software. What is the approximate price of a Kinetics Neo license? Is it an annual license or a lifetime license? Somebody is asking.
Yeah, for Kinetics Neo, for the full version, we have a following policy. We have perpetual software, license. It means that if you pay once and get it, it works for all time, for always. And if you have additional support subscriptions for 12 months, so firstly, support subscriptions 12 months is included for each new customer, and after that you can prolong it, then these support subscriptions includes the updates for free during these 12 months. And additionally, you can ask questions about consulting. You can about how to work with the software, or if you have some questions regarding your material, you can ask questions to us regarding your material inside this support subscription time. And it is optional. So there is no annual license. It is lifetime license for always.
Okay, and I'm sure if they have more questions about the software and the license system, they can just get in touch with you or maybe find it on your website. What do you think?
Yes, we have a lot of information on our website, kineticsnetch.com, and regarding the price, here on our website, there is information about a website. Here, I just go to main. Here is the main. the main page on kinetics.com, and here you say request a quote. And now you will get information about the price from your regional sales representative of our company.
Great. Yeah. Good tips and good insight. Thank you very much. So with that, Elena, I think we can wrap up our session. Everybody of our attendants has our general webinar email address. I will just repeat it once more. It is webinar_ngb@netzsch.com. You can always also reach out to this address in case you have any questions afterwards, maybe after you watched the recording in a few days. With that, I would end our session for today. Thank you for joining. Thank you for the great and interesting questions. Thank you for your time, and hopefully we see each other soon in another webinar. Bye-bye.
Bye. Thank you for your attention.